Good morning everyone. I am Shobha from 2nd MSc Mathematics. I am doing project under the guidance of Ms. Lynn Anita. My project title is Comprehensive Study of Graceful Labeling and its Extension in Graph Theory. Let's see the introduction for my topic. Graph theory is a fundamental branch of discrete mathematics that studies the structure and the properties of graph, which consist of vertices and edges. One of the most important and widely studied area in graph theory is graph labeling, where integers are assigned to the vertices, edges, or both, according to certain rules. Among the various types of graph labeling, graceful labeling occupies a central position due to its elegance, simplicity, and rich theoretical and its importance. Let's see the definition for graph. Graph G is equal to V, E consists of finite non-empty set of objects V is equal to V1, V2 up to etc. called vertices, and a finite set of objects E is equal to E1 or E2 up to etc. called edges. Each edge EK is identified with an ordered pair V1, V2 of vertices. Let's see the definition for connected graph. A graph is said to be connected if there exists at least one path between any pair of vertices. A graph can be, let's see the definition for disconnected graph. A graph can be split an independent compound, then it is called as disconnected graph. Let's see definition for vertex labeling. A labeling is a function from the set of vertices to some set of labels, which is called as vertex labeling. Edge labeling. An edge labeling is a function from set of all labels. Let's see what is graceful labeling. Each vertices is given in a distinct label from 0 to q, where q is the number of edges. Each edge labeling is the absolute difference of its two vertex label. All edge label must be different and must cover exactly the set 1, 2 etc. q. Let's see the definition for graceful labeling. Path graph Pn are graceful. Star graph K1, N are graceful. Many trees and certain cycles admit graceful labeling. Let's see theorem for graceful labeling. K1, N and K1, N are gracefully united. Proof. Assume that the vertices of a graph K1, N with U as its append vertex are U1, U2 up to etc. Un, and the vertices of another star K1, N with K as its apex vertex V1, V2 up to etc. Vn. For I is equal to 1 to up to etc. n, let G be a graph that results from merging the above star with its end vertices Ui and Vi. Let Wi be the new vertex that results from joining Ui and Vi. We define f is to V of G tends to 1, 0, 1, up to etc. 2q minus 1 as follows. F of u is equal to V, f of v is equal to 0, f of w1 is equal to 2n up to etc. f of wn is equal to n plus 1. A elegant labeling is provided by a function f mentioned above. Let's see the application for graceful labeling. Communication networks and routing. Graceful labeling is used to design conflict-free channel assignments, reduce interference by ensuring all edge labels are unique, create efficient and noise-free routing schemes. Network topology design. Graceful labeling helps construct tree-structure network, minimal interference path, unique path routing system. Let's see the definition for even graceful labeling. Let G is equal to V, E be a graph with edges. A function f is to V of G 0, 2, 4 up to etc. to q. F is injective. Each edge U, V belongs to E of G is assigned the label f of u minus f of V 2, 4, up to etc. to q. A graph that admits such a labeling is called even graceful labeling. Let's see the theorem for even graceful labeling. Supercategory SCN, N is a even graceful 1 less than or equal to m less than or equal to n. Proof. Let V0 be the central vertex of the graph. Let Vi be the first level node of the graph. I varies from 1 to n. Ui be the connector node of the graph. I varies from 1 to n. Let Uij be the path node of the graph. I varies from 1 to n and j varies from 1 to m. Bij be the pendant vertex of the node. I varies from 1 to n and j varies from 1 to m. We define f is to v of s, c n, n tends to 0, 2, up to etc. to q as follows. F of v0 is equal to 0, f of v1 is equal to 2q minus 4 of I minus 1, n minus 1. F of ui is equal to 2 plus 4 of 1 I minus 1 n minus I. F of Vij is equal to 2q minus 4 I minus 1 n minus 1 minus 2j if j is odd. 2 plus 4 of I minus 1 plus 2 of j plus 1 if j is even. F of ui, j is equal to 2q minus 4 I minus 1 n minus 1 minus 2 j plus 1 if I is even. 2 plus 4 I minus 1 n minus 1 plus 2j if I is odd. Another theorem for the even graceful labeling. Every graph that is evenly graceful is elegant. Let G be a vertex labeled even elegant graph. F is to v of G tends to 0, 2, up to etc. to q. Create a new label. G of v is equal to f of u divided by 2. Next, labels from 0, 1, up to etc. q are assigned by G. Each labels become G of u minus G of v is equal to f of u minus f of v divided by 2. Thus, the label G is elegant. Therefore, we demonstrate that all graceful labeling are graceful. On the other hand, every graph that is elegant is also graceful. Let's see the definition for all graceful labeling. Let G is equal to v, e be a graph with edges e is equal to q. A function f is to v, g tends to 0, 1, 2, up to etc. to q minus 1. F is injective. Each edge uv belongs to E of g is assigned the label f of u minus f of e. Edges from 1, 3, up to etc. to q minus 1. A graph that admits such a labeling is called odd graceful labeling. Let's see the theorem for odd graceful labeling. A complete graph K4 cannot be a subgraph of an odd graceful graph. Assume that K4 contained in G, where G is odd graceful, K4 has 6 edges, odd labels are necessary, 1, 3, up to etc. 11. There are several triangles in K4. Give to the parity limits on 4 vertices, employing only odd differences. Necessitates the duplication of edge labels. Strange, elegant situations are constructed by this. Consequently, K4 can't be oddly elegant. Let's see the application for graceful labeling. Application in biology and medicine. In a biological and medical disciplines, graph theory is crucial. The human brain's neural network can be represented as graph with symbolic connection acting as link and neuron as nodes. Directed graphs are also used to analyze predator-prey dynamic in food chain and ecological systems. Graphs are used in epidemiology to simulate the spread of illnesses and pinpoint crucial nodes that affect transmission. Additional biological uses of graph theory include protein interaction, neutron networks, and gene regulatory networks. Let's see the application in chemistry. Molecular structure are represented in chemistry using graph theory. Chemical bonds are shown as links and atom as nodes. We refer to this prediction to Molecular graphs. Cyclic compounds are represented by tree graphs, whereas ring structure like benzene and cyclones are represented by cyclic graphs. Molecular stability and chemical characters can be analyzed with the use of graph invariants like degree, sequence, and connectedness. In chemical database, graph theory techniques are employed to avoid ambiguity and uniquely identified molecular structures. Let's see the conclusion for my topic. Graceful labeling and its extension play a vital role in understanding the structure and properties of graphs, especially trees. These labeling techniques have both theoretical and significant and practical application in areas such as network design and security system. Thank you.